Hey folks, sorry, forgot my pen. So I'm going to help you out here if you were stuck on this thing on how to put it all together, because we learned how to determine the intervals when a function was increasing or decreasing in section 4.3. We figured this stuff out in 4.4, and we kind of want to put it all together, and it gets, it gets pretty big. So I'll show you on number 1 how you would do it, and then you can try out 2, 3, and 4, which are very similar. Then I'll show you what I want on 5, and you can do 6. So just to get you going here. So first of all, I'm going to need a table for both of these, but I can do it all in one table. But I know before I get going any further that I need to find critical numbers. And I'll eventually need the first derivative and the second derivative, so why not do it right away? So first things first, I'm going to take the derivative of this, 3x squared minus, and then this is 12x, and the 4 goes away. And the second derivative, might as well keep on keeping on, right, while I'm going. So I have 6x minus 12. Okay, so those are kind of like I'll put this in a box because I'll use those later. All right, and later comes up pretty fast because I want to make a table with all the values, but I need to know where to split my graph and how many splits I'm going to split it into. And guess where this is going to split? The graph will split at critical numbers and inflection points. The graph will split at critical numbers and inflection points. So that brings up the next question. Oh, what the heck are critical numbers? You should remember that critical numbers are when the first derivative, is 0 or undefined. So I take my first derivative and I set it equal to 0 to find out these critical numbers. And if you recall, critical numbers are where the derivative is 0 or undefined. And what do they figure out? They find extrema, and sometimes they accidentally find inflection points. But usually they're made to find extrema, which are your max and mins. So when I solve this, I'm going to solve it by factoring because there's a GCF to both of those. If I take out 3x, I'll have x minus 4. And this leads to an answer of 0, and this leads to an answer of 4. So I already have 2 places to split my graph, but I want to check, are there any inflection points? Because these are my critical numbers. And if you're wondering, why did you only set the derivative to 0 and not undefined? Well, I didn't have to because I used my good old experience and said, well, this is not a fraction, so I'm not worried about it being undefined. It's not a radical, so I don't really have places to worry about. If you don't see fractions, you're not going to have that undefined thing in your derivative. If you do, like here, I would be worried about when the bottom is going to equal 0 in the derivative, and sometimes it does and sometimes it doesn't. So just because you see a fraction doesn't mean the bottom will ever be 0 either. I think number 2 you'll find out. Anyway, so I found critical numbers. That's where my graph is going to split, here and here. We'll figure out whether they're max or mins in a minute. We have a couple ways to do that. And the other one I want to find out is inflection points. And inflection points are when the second derivative is 0. You don't have to worry about undefined. Oops. Second derivative equals 0. They're undefined and a second derivative doesn't mean anything. So I take this guy and set him equal to 0. And I move the 12 over, and I get 2. Okay, see, that's good I did that, because otherwise you would be missing some stuff. So now my graph is going to split at 3 places. 1, 2, 3. Okay, it's going to split at x equals, I try to put them in order, so 0 is the farthest left, then 2, and then 4. They don't always come out that even. And then we're going to chop up our whole graph interval into those pieces. So from negative infinity to 0, it's going to behave one way. From 0 to 2, it's going to behave another way. I'm just splitting it. from 2 to 4, and from 4 to infinity. What's crazy is you don't have to worry about it like changing its concavity or changing its increasing, decreasing after that. Shoot, I wish I wouldn't have written so close to that. Okay, so after your interval is picked, you need to pick a test point in each interval. And a test point is anywhere between there and there. So I always try to pick the smallest one that I can. Like -1 is in between those two numbers. How about 1 is on this interval? 3 is here. By the way, like what if you ever had 0 and 1? You can do 0.5. You can do decimals. I could pick 3.999. It's on this interval. I'll get the same answer. And remember, the reason it doesn't matter which one I pick is any one of those numbers you pick between in negative infinity and 0 will result in the same thing in the end. Okay, I got to do this just so I have room to write. Okay. Anyway, so my next column, after I chopped it into pieces, I wrote the intervals, I found my test point. Then I want to do two things now. I want to do a check with the first derivative, and then a check with the second derivative, and then a picture. Okay, so let's do this. If I plug a -1 into my first derivative, I just need to figure out if it's positive or negative. I don't care what number it is. I'm going to put a -1 in there, and I'll get +3 and +12, so I get a positive answer. If I put a regular 1 in here, I get 3 minus 12, which is a negative answer. If I put a regular 3 in, I'm going to have to get a calculator and do these real quick. So if I put a 3 into the derivative, remember you're doing the first derivative, I get a -9, so it's negative. And then if I go back up and put 5s in there, right, I only care if it's positive or negative. I get a +15. So remember, your first derivative tells you if it's increasing or decreasing. So my graph is going up, it's going down, it's going down, it's going up on those chunks. Okay, so now my second derivative tells me if it's concave up or concave down. So I'm going to do the same exact thing with this test point, but I'm going to be plugging it into the second derivative. So if I put a -1 in here, I get -6 minus 12, which is still negative. That's concave down. Okay, if I put a +1, I get 6 minus 12, which is negative. So we got concave down. If we plug a 3 in, I get 18 minus 6. That's +6. And that's concave up. And my last one, if I put a 5 in there, I get a positive for sure. Okay. So, what does this mean? Well, draw a picture of each one of these. And I got a little tip for you how to draw a picture. So, hold on, let me get a pencil. Here's what I suggest you do. With pencil, first I draw, what does increasing look like? Don't give it any curve at all. Just draw, okay, increasing means uphill. And then you bend it. Okay, so I always draw a straight little stick first, and then I look at the concavity to bend it. So if I bent this so it's concave down, my graph is going to look like this. Okay, it's going to have that downward shape for this whole chunk of the graph. Isn't that crazy? The next one, because I can erase the old line, the next one is decreasing, so that's downhill. And then I make it concave down like a frown. So I add in a little darkness here. It's going to look like that. And then the next one is decreasing. So I draw a stick going down. And then I bend it so it's concave up. It's going to behave like this. I can erase the old sticks. Okay. I find less mistakes are made if you do a stick first. The last one is an increasing stick. And then I bend it so it's concave up. Right? So my graph is going to look like that, which is crazy you can be that accurate. I also know by looking at this, I know if it goes like this, you imagine those two connecting, we have a max at 0, something. If it goes from concave down to concave up, this is an inflection point, which we already knew, at x equals 2. And if it goes from down to up, decreasing to increasing, I know that I have a min right here at 4, something. It's kind of crazy you can figure that out. And if you plug in these numbers, I'm going to pause it and do that so don't waste your time. So yeah, I plugged them in. Make sure you're plugging the x values into the original equation to get the points. So I know there's a max there, an inflection point there, and a min there. And what's kind of cool, that's crazy that we can tell all that stuff just by using a couple derivatives and setting them equal to 0 and knowing what we're doing with that. And here's a graph of it. I just typed it in. I made my window so you could see the stuff. But if you look at it, it's concave up, or concave down but increasing, concave down decreasing, concave up, switches right here. So I have a max right there. I have an inflection point at 2, -12, right about there. I have a min at 4, -28, and then it's concave up the rest of the way. But we already knew that was its shape. That's the only shapes. You don't see any other wiggles, which is kind of cool. All right, last thing, I'm going to flip this over and just show you what we're doing here. I'll help you with 5, and then you can figure out what to do on 6. So first of all, when you see f of 0, that means my regular function has a 0 y value. When x is 0, y is 0. So I'm going to put a dot there. It also has a 3, 0. Those are x-intercepts. They could have written it like this. Right? That's what this relates to, and that's what that relates to. But we figure you know function notation at this point. Okay, I could have given you any point. If I would have written f of 1 equals 5, that would be the point 1, 5. That's not really on this graph, so I'm going to scribble that out. All right, second thing is, I have these two dots. I know my graph first derivative is positive if x is less than 1. That means I'm increasing the whole time x is less than 1. And then I'm decreasing the whole time if x is greater than 1. So I go from uphill, right? Increasing is up, decreasing is down. I go from uphill to downhill, and it switches over at 1, which means that must be a max or a min. And if you think about it, if it goes from up to down, it's a max. The other way I know it's a max is look at my second derivative. The whole time it says the second derivative is less than 0, which means concave down. So it's down like a frown the whole time. So I know there's a max at 1. I don't know how high it is because they didn't tell me the point. Let me just pretend it's like this high. I don't know if that's exactly what it was look like, but this is, from what I know, I have two x-intercepts. I know there's got to be a max at x equals 1 because it goes from increasing and decreasing. And I know it has to be down like a frown the whole time. So you're going to do that same thing here and kind of figure out what the graph is going to look like. And you're just, doesn't have to hit at that point, but I did have to have this shape to it. And I knew there was a max or min at x, so I tried to make it the highest point right there. Anyway, hope that helps. These problems, they take some work, but they can make pretty cool graphs. So, all right, talk to you later, people.